All right, good morning, differential equations people. So today we're going to talk about section 2.4. Right? So let's go ahead and make sure I can draw. Good. So let's see, 2.4, these are exact d's. Okay, now at the beginning of the class, I kind of promised you that there wouldn't be partial derivatives, and I lied. So there are partial derivatives. And this is the section that we deal with that. I'm not saying that will never come again, but this is one of those sections where this had this. Okay, so here we go. If you recall from Calc 3, and I can hear you now, but I didn't take Calc 3. Like, I know, that's why I used the word recall. We're going to have u is equal to some function of x's and y's. And we'll go slow at the beginning. Okay, I promise. So, we're not going to be, I'm not going to prove these things to you because that's what Calc 3 is for. But we're going to talk about something called partial derivatives. Okay, but you'll catch on pretty quickly. This is not a terrible thing. Okay, and furthermore, I don't know if you remember what the total derivative is. Okay, but a total derivative is du is equal to the partial of u. This is what the partial symbol looks like. It's kind of like a 2, but sort of, kind of, or a d. It's the d, but it's like a little tail at the end of this thing. Okay, that's a terrible d. But usually that's how I tend to write it. Okay, so it's almost a 2, but not quite. So the partial of u with respect to x, okay, dx, plus the partial of u with respect to y, dy, that would be the total derivative. Okay, and it's not important that you memorize this from Calc 3 or not. Okay, we're just reminding you of it right here. Okay. We could also write this in different ways. You'll see it f with a little x here, okay, seeing that they took the partial of x here, dx, plus f, and then put a little subscript y, dy. Okay, so that's another way of writing it. That's really the notation that we have to deal with. Okay. And usually we're going to be dealing with the fact of u is equal to some constant. If you go to Desmos and type in something like x squared plus xy plus y squared equals 110, okay, you're make it sure it's a negative, it's not a negative number. Well, I guess, no, okay. You'll see it. If you don't put the 10 in here, if you don't say equals 10, it won't graph it. But if you put the equal something, it'll graph it. Okay, so usually we want something like f of xy is equal to some constant. And then we're going to apply the total derivative, meaning the right-hand side gets to be 0 because derivative of a constant, even with partials, is still 0. Okay. So that's kind of the setup that we're dealing with. Okay, so we want du by dx dx plus du dv, or sorry, dy, dy is equal to 0. That's kind of the format that we're looking for with these things. Okay. Let's see. So I'm going to start my example here, and within my example, we're going to, well, actually, let's do an example of what a partial derivative is. Okay. When we're taking our partial derivative, what we're going to do is we're going to be treating the y as a constant. Okay, so if I have, like, say u is equal to x squared y plus y squared x, let's put a sine x here and plus a cosine y. Okay, so if I'm taking the partial of u with respect to x here, okay, so we're going to take our x's, treating y as a constant. Okay, so the idea here is we're going to hold y constant and just take the derivative with respect to x. So this is going to be 2x and then y is a constant. Okay, so we have a constant times x squared. We have 2x times that constant. Okay, plus we have derivative of x here, so that's just going to leave y squared. Derivative of sine x is going to be cosine x. And then cosine y, like cosine y effectively is considered a constant with respect to x. Like y doesn't care what x is doing. Okay, so this is just going to be a 0 here. Okay, you don't have to write the 0, just trying to make a point, because this is like maybe the first time some people have seen this. Okay, and the same thing, we're going to do partial of u with respect to y. We're going to hold x constant. Okay, so what we're going to do is we're going to go ahead and say, well, let's go ahead and if we have that, that's right, x squared is constant. It's like having 9y, right? 9 is a perfect square, so 9y would be, we just have 9. And then this would be plus 2xy, okay? Again, sine x does not, y is not carrying what x is doing, okay? So that's considered constant. And then we have our minus sine y, okay? And that would be our two partials with this. Now, just like in Calc 1, when you took like one derivative, then they said, well, we could have more fun. We could take second derivatives. Well, with partials, second derivatives go kind of nuts, because you could have the second derivative of u with respect to x squared. So we could take another derivative here, right? This would be d by dx of du by dx. We could do that. That's another partial with respect to u, with respect to x rather. So we can just take more derivatives here, or we could take d squared u dy squared, which would be d dy du dy. Okay, so we're taking the derivative, partial derivative with respect to y of this function here. Okay, or we could take the second, and we could have said, well, and this is going to be d by dy of du dx. So what this means, right, is that we have a function here, right, of x's and y's. This is our function, du by dx. We're going to take this function and we're going to take this derivative with respect to y. Or, and this is the last one, we could do d squared u dx dy, which is dx and then du dy, which means we're taking the derivative with respect to x, right, of this function here. These are the two that we really care about as far as this class goes. When you take Calc 3, you'll be doing all of these, okay, because they're useful for optimizations. So if you haven't taken Calc 3 yet, this is the joy you have to look forward to. All right, so we can all enjoy that when we get to it. Okay, so let's go ahead and let's determine, okay, d squared u of dy dx. So what I'm going to do is I'm going to take the derivative with respect to y of du dx. Okay, so we're going to take the derivative with respect to y of, what was this? This was 2xy plus y squared plus cosine x. Okay, now remember, we're taking the partial with respect to y. Okay, so this is a partial with respect to y. We're treating x as a constant. Okay, so when I take respect to y, this is like, 6y. So the derivative of 6y would just be 6. So this is going to be 2x. Okay, taking the derivative with respect to y, that's going to be 2y. And then we're taking the derivative with respect to y of cosine x. Well, cosine x doesn't really care what y is, y does not care what x is doing here. So we're done at this point. Okay, and now we're going to turn it around. We're going to say, well, how about d squared of dx dy? Okay, so this is d dx, right? Du dy, which is dx of, and then we'll go back up to our y's. Okay, and this was x squared plus 2xy minus sine y. So this was x squared, what was that, minus 2, minus or plus? Should be a plus, okay. Plus 2xy minus sine y. Okay, so again, we're taking the derivative with respect to x, okay, holding y is constant. Okay, so y is considered constant. Okay, so that's, that's like the first derivative you learn, right? That's 2x, okay, minus, or plus rather, plus. And then we're holding y constant, so we're just taking the derivative of 2x, really, right? So just have 2y here, okay. And then, again, y doesn't, x does not care what y is doing because y is considered constant. So this term here, that's constant. So that's just going to be 0. And then I want you to make an observation here and say, wait a minute, these look awfully similar to each other. Yes, they do. Will they always be the same? I'll put a question mark here. Are they always equal? No. Okay. So for the most part, because I remember taking a physics class, and they would swap these all the time. They would say, oh well, we're just going to do this. And they would just swap the order of differentiation all the time because one problem was easier to solve than the other. And about 2 weeks into the class, I was like, you can't, that's not guaranteed. He's like, well, for this class it is. Okay, so that's like, but you can't do that. Like, technically you can't. You can if the first partial. So if this thing here is continuous, then you may swap the order. Okay, if this is continuous, you may swap the order, and they will be the same. Okay, so it doesn't matter. So yes, if df or du by dx and du by dy are continuous. Okay, there are a couple of examples, and there you can almost smell like this is going to be a problem. Okay, because they're piecewise functions, right? They're defined. They give you f of x, y equals, and then they do one of these guys where it's like it's equal to this thing here, but it's equal to a different thing there. Then it's not going to be guaranteed. You're not going to get the same answer. So I want you to be real careful. People screw this up all the time. They're always equal, because in textbooks they are, because it makes the rest of our work done very nicely. And for most situations, it's not an unreasonable assumption to make that these are going to be continuous and we're not going to have a problem. And even it's like, but that's not a continuous function. Okay, I'm gonna pull something called the no nonsense principle. For those of you in linear algebra, you're probably learning something called matrix multiplication now. And if you have matrix multiplication, you're going to do various things with it. This is not true, by the way, right? Can't do that. We pretty much restrict does the multiplication exist? Can you do it? And if you're going to pick two matrices that you can't multiply together, then we aren't going to consider that situation. Okay, we kind of do the same thing with regular numbers too, right? If you have two values, two things, you say, well, they commute. I'm like, well, look, if A is purple and B is Tuesday, I don't know if purple times Tuesday is the same as Tuesday times purple. I don't know. Okay, these are not defined operations. We don't have things for that. They might be. Okay, there's a whole set of math called group theory where you can make that stuff up. Okay, I don't know what it means, and I don't know why you would do it, but there's rules. Okay, so you can construct it. But like I said, we're going to restrict ourselves to this is going to work for us. Okay, we're not going to consider the cases where they aren't. And if you ever do, like, is it always going to work? Like, no, it's not always guaranteed. It's just guaranteed when the class finds it convenient to make it so. And again, like all my engineering classes that I took, all the physics classes I took, they didn't even bring it up. He's like, of course they're the same. I'm like, no, they're not. They have to be continuous. This has to work. I'm like, well, those are functions that we don't deal with in real life, so we don't worry about it. All right, that's fair, but say something. All right. So with that out of the way, I've said something. We're only considering the cases where this is going to be true. But I just want you to, I want to warn you, if you take a more advanced math class, that this is not always going to be the case. So don't think, well, this is always true. No, it isn't. Okay. All right. So let's go on to, we're trying to solve a differential equation here. So let's get back on track for that one. Okay. So let's see here. Looking at my little example here. Okay. Did I write down my little example? Of course I didn't. All right. So, all right, there's what we're going to do. We're going to say, how about we do an x squared minus a 3xy plus 4y squared is equal to c equals 10. Okay. If you go off to Desmos and type this thing in, you'll get a fancy little ellipse. It's kind of cool. And I will go with that. Okay. So what I'm going to do is I'm going to find the total derivative here. Okay. So we're going to say du by dx, right? That's going to equal taking the derivative with respect to x. So it's going to be 2x minus 3y. And then since y is here by itself, it's considered to be a constant. Okay. So we're just going to put a little dx here. And we're going to say du by dy. Okay. So constant, right? Because we're talking derivative with respect to y, so it's going to be constant. So we're going to have a minus 3x, right? Because y is a constant, or we're taking the derivative with respect to y, so this guy here is a constant. And then plus, it looks like we have 8y, okay, dy. Okay. So here's what's going to be given to you. Like here's the first line of your problem, okay? Is they're going to say 2x minus 3y dx plus negative 3x plus 8y dy is equal to 0. And they're going to say solve the differential equation. Okay, I started with the actual function because at the end of this, I want you to see that this process is going to give you back to the original problem. Okay, the original equation. Okay, now typically they call the part that's attached to the x m, and the part that's attached to the y n. So the first thing we have to do here is we have to check. Are these exact? Your book will lie to you. Okay, they will say solve this differential equation or say that they're not exact. Okay, so if they're not exact, great, you're done. But if they are exact, then you've got some work to do. Okay, so can we solve it? So we're going to check. So what we're going to do is we're going to say, well, this was obviously, sure, the total derivative of something. Okay, so what we're going to do is we're going to take dm by dy and we're going to take dn by dx. Now, since m, right, that was the partial with respect to x, really what we're doing here is we're saying this is dy of du, some function, right? This is x, is the derivative, the partial of u with respect to x. And dn, right? dn was, or n was du dy. And we're saying, is this the same? So what we're doing is we're checking, right, the cross variable partial derivatives, the second derivative with the mixed variables. Okay. And in here, right, we're taking this one here. So this is 2x minus 3y. We're taking the derivative with respect to y. Well, if that's constant, and then taking the derivative of negative 3y, well, that's negative 3. So that's not so bad. Okay, like I said, I wanted to pick a nice easy one to start us with because, some of you may or may not have seen partials. Okay, so dn by dx, right? we're taking the derivative here with respect to x, so that's going to be negative 3. 8y, that's with respect to x, that's not, that's not going to do anything for us. So that's 0. Hey, these are the same. You have to check, okay? So if dm dy is not the same as dn dx, you're done. It's not exact. Okay? If they say to you, hey, solve the exact equation, right? And I will say something like solve the exact equation. The first thing you're going to do is you're going to check this, and if they don't match, then I lied to you, right? This is not an exact differential equation. You need different techniques. There are different techniques, okay? We talked about having integration factors in the previous section. There are integration factors for this too, to kind of force the issue. That's a little beyond what this particular class does. Some ODE classes and some colleges work this through. We have way too much other stuff on our syllabus to do this, so we don't go into it. Okay, just want to make you aware that those exist. Okay, so yeah, they're the same. That means that they are going to be exact. Okay, so what we're going to do is we are going to integrate. So our next step here, so 1 is check, 2 is we're going to integrate. So what we're going to do is we're going to integrate m with respect to x. Okay, so we're going to do this. We're going to do n dy, just like it says, right? I mean, we have n dy, we have m dx. We're just going to integrate them. Okay, so this is going to be, right? We have, what do we have? We have 2x minus 3y. Okay, and here we have negative 3x plus 8y. And we're going to integrate this with respect to y. We're going to integrate this with respect to x. Okay. So integrating with respect to x, right, we just get x squared minus 3. Remember, this is a constant, so xy. Okay. And then here, right, integrating with respect to y, we're going to have negative 3xy plus, and then we have to integrate y, so it's going to be y squared over 2. 8 over 2 is 4. But we're not quite there yet, because when I took my partial, if there was some stuff with like, every book uses J for Y, so I'll try to be consistent. So if I took this function and I differentiated it with respect to x, partial derivative with respect to x, this y term, this is 0. So when we integrate it with respect to x, we got to make account for the fact that there might be some function of y that was here that was just lost when we took the derivative because it was considered constant and washed away. Same thing with this one. We have some f of x. Okay. Now here's what you do. Okay. So this is really it. Say, which ones are the same? These are the same. So my function includes this. We need a function that is purely a function, right, of x's here. What's that going to look like? We'll do that one. Okay, so look, here's an f of x. Hey, there's a function with just x's in it. We should match those up. And yeah, we do. Okay, and the same thing, right? You have a function with just g's in it. Here's a function with just, function with just y's in it. Here's a function with just y's in it. We should match those up, and then we do. So our function that we're coming back to here, right, is we have our x squared minus, we only need one of these, okay? I know it lists twice, but we only need the one of them. And we have the 4y squared equals some kind of a constant, and that's what we're getting back, okay? So the differential equations part is, here, we start with the differential equation, and we come back to the original function. This is the reason why I gave you the original function, was so we could look at this and say, oh, wait, that's pretty much what we got as an answer. And that's what I want you to see out of this, okay? So that's how you do exact. Okay, that's how you solve an exact differential equation. So let's see here. We do some examples. Okay, one. Okay, that might help out a little bit. Okay, and it's pretty much always the same two steps. We check to see if it works, and then we take the integrations by themselves as we go. Okay, so I'm gonna pause for a cup of coffee here. So, all right, there we go. So let's do a couple of examples. All right, so let's see here. We are given, so we're going to say x squared plus y over x. I guess it's y over x squared here. Dx, okay, plus, what do we have? Y squared plus ln 5x dy is equal 0. Okay, so here's our m, here's our n. Okay, so the first step here is we have to check to make sure, are these exact? Okay, so what we're going to do is we're going to take dm dy, right? We're going to take this derivative with respect to y. And let's see here, it looks like we get 0. And then we have 1 over x squared times y, right? This is 1 over x squared times y. Taking the derivative with respect to y, we have 1 over x squared. Okay. And with n, say, well, dn dx, right? So this is going to again be 0, and then natural log. This is natural log of 5 plus natural log of x, isn't it? Right, that's what natural log of 5x is. And natural log of 5 is a constant. Natural log of x is just 1 over x. So this is equal to 1 over x squared. This is equal to 1 over x. Are these the same? No, they are not. I can't believe they lied to me about making sure I could solve this. So this one is not exact. You're done. Okay. The wording of the problem is going to tell you, like, solve the exact equation. If it isn't exact, press, say not. So solve exact. If not exact, say not exact. Okay. I'll show you the kind of problem that I'll ask you for the quiz toward the end here. I think we have it. I'll show it to you now. Problem number 8, which I actually don't have an example of doing. I guess we could. This is like my favorite way to ask you this question, is find the value of k so that the differential equation is exact, and just put a k in here so that you guys can force the issue. And then I'll say, and solve it. Okay, so that's pretty much how I ask this question, because there's a lot to keep track of in the differential equations class. And I'll go into that in a little bit here as we're walking through this. So let's see, how about this one? We have cosine x plus ln y dx. And again, we're only talking about the region in which this is a continuous function. Same thing here, like I wouldn't pick x, whatever we had here, whatever region this would be good for, x would not be equal to 0. Okay, so you can pick any region where x is not equal to 0. So we could pick the region, like we have, the space r squared where x is greater than 1 and y is anything. Okay, so we could pick that part of the real plane where just x is bigger than 1 and y is the whole, negative infinity to positive infinity kind of a thing. So same thing going on here, right? Y is not 0. Okay, so any region where y is not 0 is going to be fine. Okay, plus, and then let's see, we have a xy plus e to the y dy. Okay, and again, any region where y is not equal to 0 is a valid region for this thing to be continuous. Okay, so they'll sometimes specify that, sometimes they'll just assume that, no nonsense principle, so you would know, like, if we picked something like, the region where x was any real number, but y was, say, strictly positive. Okay, so on the xy plane, that would just be this stuff. Okay, so that's what they're that's what they're doing with that. Oh, and equals 0. So check. Right, here's my m, here's my n. Okay, so what we're going to do is we're going to take a look at dm dy, and that is equal to d dy of cosine x plus ln y. So remember, we're taking the derivative, partial derivative with respect to y. X has no say here, right? X is considered to be a constant, so that one's 0. Just take the derivative of y, or natural log y rather, we just get 1 over y. Okay. Same thing, we're going to take dn by dy, so that's dx, not dy, dx. I want to take those partials. Here we have of x over y plus e to the y. So this is, right, taking partial with respect to x would be like 1 over 3 times x. So this is going to be 1 over y. Taking the derivative with respect to x, the y, e to the y, we don't care. So look at this, we see they match. So check, this is exact. Okay. So now we actually have to go ahead and integrate stuff. So we're going to go ahead and we're going to integrate cosine x plus ln y with respect to x. Okay, so that's going to be pretty nice. That's great. That's sine x plus x ln y, right? If you had ln 3, take the integral of ln 3, we get x times ln 3. Okay. So, plus some function that might just be with y's in it. Okay, nothing else. No x's. Okay, same thing on the other side. We're going to look at this one. Excuse me, x over y plus e to the y. And we're integrating with respect to y. So let's see, that's going to be x ln y plus e to the y plus some function with just x's in it. Okay, so if I took the partial here, right, partial with respect to y, we come back to right here. Okay, so again, we're going to go ahead and match things up. Okay, so we need g of y. Can I find any functions with just y's in them? Yeah, sure can. And what about just functions with x's in them? Right? So look here, we have x, we have sine x. Okay, and then we have a piece that matches, right? A piece that's common between them. You don't have to add them. Okay, we're just going to break the whole thing together. So we're going to have sine x plus x ln y plus e to the y equals some constant. And that's our solution for this exact differential here. Okay. Let's see here. It's the same one I just did, isn't it? That's close enough to it. I'm not going to do that one. You could do this one, though. Oh, yeah, this is beautiful. Okay. All right, so let's go ahead and check this one. This was a y squared cosine x minus 3x squared y, okay, minus 8x dx plus, okay, we have 2y sine x, okay, minus, what is this, x cubed plus ln y dy is equal to 0. There. It's a delightful looking problem, isn't it? All right, so we're going to check. Okay, the instructions will say check to see if it's exact. If it is, solve the differential equation. Okay, so the first thing we're going to do, right, we'll identify that as an m, that is an n. So we're going to check, right, dm by dy. So we're taking the derivative with respect to y. The cosine of x, that's a constant. So we have 2y times cosine x, okay, minus 3x squared. And since we're taking the derivative with respect to y, the negative 8x, that's 0, okay? And we're going to say dn by dx. So that's going to be 2y is constant. So the derivative of sine x is just cosine. So we have 2y cosine x, right? Minus 3x squared, because we're taking the derivative with respect to x here. So derivative of x cubed, right? 3x squared. And then this natural log, that's this just with y's in it. So that's, that's 0. So we look and say, hey, look at that. They're exact. Okay, so you're good to go to solve this problem. Okay, so let's go ahead and integrate m, right? So we're just going to integrate m dx. So that's the integral of y squared cosine x. There's a minus, right? Minus 3x squared y minus 8x. Yeah, I think we're okay. Okay, and that's integral with respect to x. So integral of, right, y squared's constant, so integral of cosine is just sine. So we have, this is y squared sine x minus, y is constant, so we're just going to get 1/3 x cubed times 3, so minus x cubed y, and minus, it looks like 4x squared, plus some function with just g in it, or just y in it, rather. Again, for those of you in linear algebra, you're going to do linear transformations a little bit later on, and then you're going to undo linear transformations. You're going to come back, and the thing is like when you have a transformation of something, right, and it ends up going to 0, when you try to inverse that, right, you have to bring back everything that possibly could have been at 0. So everything that could have gone to 0, you have to bring that back with that inverse transformation. That's what we're doing here, is we're bringing back everything that could have been mapped to 0, okay, which is any function that would have had a y in it. Okay, so when you get to the part about kernels, that's what they're talking about. Okay. Okay. So let's go here. We have, what is this? We have 2y, so this is 2y sine x minus x cubed plus ln y dy, and this is going to be, right, y squared sine x. We have minus x cubed y, okay, because we're just, this is just a constant, okay, and then this is a plus, it is a plus. And then we have to remember, like, how do you integrate natural log y, right? If I just look down here, we say natural log y dy. And this was like the canonical case of, this is why you learned integration by parts. So we say let u is equal to ln y, du was 1 over y, dv was equal to dy, v was equal to y, and then we draw the little box, right? So this is going to be y ln y, that's this part, minus the integral of y times 1 over y dy, okay, the dy here, right? So this was y ln y, these two guys cancel, so it's a nice physics integral, right? Integral of dy is just y, okay? So that's this one. So we're going to have plus, and then we have y ln y minus y, okay, plus some function with just x's in it. All right. So which parts match up, and which parts do we have to like mix and match for the ones we don't have? Okay. So I need a gy. I need functions with just y's in them. Oh, look, here's a function with just y's in it. And then same thing, right? We need a function with just x's in it. oh, here's a function with just x's in it, and notice the rest of these pieces match. Okay. So we're going to have y squared sine x minus x cubed y plus, oh, I'm sorry, we'll say plus, y natural log y minus 4x squared, and that's equal to some constant. That is the solution to this exact. If I did the total derivative here, we get back with what we started with. Okay, so there's our solution for that. And oh, were we done? We were for the problem I wrote down, but for the problem I got this from, they told us that y of 0 was equal to e. So when x is 0, y is equal to e. Okay. So if I plug this thing in, right, we get e squared times sine of 0 minus 0 cubed e plus e ln e minus 4 times 0 squared is equal to our constant. Well, sine of 0 is 0, so that's gone. 0 cubed times e is still 0. Natural log of e is 1, so this is e minus e. Well, that's conveniently 0, and then that's all 0 equals c. So not much of a surprise there. C is equal to 0. I should say not anything remarkable here. So we're just going to rewrite this. Let's see. There's our specific solution there. Okay. So you'll see this a couple of times and they'll do this to you, but just remember, like, take it apart, right? X equals 0, y equals a. Okay, and we're just trying to solve for c for that one. Okay, I'm going to go ahead and stop this one now because I think that's pretty much all we're going to say about this. Pay attention to, problem number 8. Okay, I mean, this is kind of nice because it's a, these are usually polynomial type of derivatives, so they're not, most of the problems I find like this, they're pretty tame as far as the calculus goes, and you just have to match these guys up. Okay, so, and it tells you, it's like, hey, find it so it's exact, so you're not wondering, I'm like, what kind of a differential equation is this one? What technique should I be using? It's like, well, it says exact, so use that one. Okay, and that's another one that I watch this happen a lot with students, is especially the statistics. Like, I'll say, do the specific technique. Like, I'm doing a different technique. I don't care what you said. Like, that's not going to help. Okay, it's just gonna make you sad. It's gonna make me sad. Everybody's gonna be upset. So like I said, I like this one because it tells you it's exact without necessarily saying to you it's exact. And yeah, and they're pretty tame problems. So I'll make sure you do this one, or when we do it, I'll make sure that there's one in the 10th edition that mirrors this. Okay, so on that note, I'll go ahead and stop and let you guys do some work.